Alright, so in this lesson we're going to start looking at a collision between two balls, and the diagram at the right shows two balls, M1 and M2. While we don't know how big M1 and M2 are, the diagram seems to imply that M1 is bigger than M2 because it's bigger in size. And so before the collision, M1 is moving down and to the right, and M2 is moving down and to the left. During the collision, M1 puts a force on M2, F21. M2 puts a force on M1, F12, and then after the collision, M2 is moving down to the right and M1 is moving down into the left. So let's apply impulse momentum theorem to see what's actually happening in the system. So we get kind of a messy equation here. What we have is some forces that are external forces here. I'm just going to call them W1 and W2. And then some forces that are internal forces over here. These are the forces that are actually happening in the collision. Here is the final momentum of both the balls added up, and the initial momentum of both the balls added up. So change in momentum of the system is equal to, all the forces acting in the system times the time. So these I'm going to call the net external forces, just W1, W2, whatever forces are happening to M1 and M2 that are not the force of collision between M1 and M2. Now it's worth pointing out there could be other internal forces if M1 and M2 are electrically charged. Maybe there's either a force of attraction or force of repulsion that might be another internal force here. So here are all the internal forces. In this case, the only internal force that we have are the forces of collision acting on both the objects. Now if we look at by Newton's third law, if these two masses collide with one another, these two forces have to be the same size but opposite in direction. So internal forces should all cancel out, and this should be true for any internal forces on these objects. By Newton's third law, internal forces between objects should be equal in magnitude, opposite in direction. So what really we have is that the sum of all the average external force acting on the objects is equal to the final, or times time of the collision is equal to final momentum times or minus initial momentum of the system. Now if there's no external force that acts on the system, so let's say that all the external forces acting on the system cancel out. Maybe these two balls are rolling on a table, so the two external forces that act on each ball are weight or gravity and normal force, but weight and normal force for each of the balls cancels out. You get the expression that zero, sum of all the external forces, 0 times delta t, doesn't matter how long the collision happens. So 0 times delta t is 0 is equal to final momentum minus initial momentum, or we could say initial momentum of the system is equal to final momentum of the system. Or m1v initial 1 plus m2v initial 2 is equal to m1v final 1 plus m2v final 2. This is a statement that's called conservation momentum. If all the external forces acting on an object cancel each other out, then this statement is true for that collision. Now we're really mainly concerned about external forces that are acting during the collision itself. So a force like friction or air resistance probably acts with such a small amount of force that it really doesn't do enough to the momentum during that time of collision to really change what the momentum is. Like I said, if these things are rolling across a table, really probably the only external forces acting on an object are weight and normal force, and those would cancel each other out on a horizontal table. So let's look at an example problem where we have two cars of a freight train being coupled. And so you have car 1 and car 2 both traveling to the right. And car 1, we have a mass of 65 times 10 to the third kilograms, moving at a speed of 0.8 meters per second to the right. And car 2 has a larger mass and moving at a larger speed to the right. Car 2 eventually catches up to car 1 and collides with car 1 and then couples to it, meaning that they are moving together after the collision. So this is neglecting friction during the collision. What is the velocity of the cars after they've been coupled? Now it's worth pointing out the only two other external forces that are acting on M1 and M2 in this case are weight and normal force, which cancel each other out. So here's some known pieces of information: M1, M2, V01, and V02. The unknown piece of information is V final, but what we do know about V final is that it's the same for both cars because they've been coupled together and they're moving together. So let's take and apply conservation of momentum. Here's my relationship. Initial momentum is equal to final momentum. So initial momentum is equal to momentum of object 1 before the collision, m1v initial 1, plus momentum of car 2, m2v initial 2. Final momentum is m1v final plus m2v final. So we can do some algebra. We can factor out v final over here, since it's the same, and divide by the sum of the masses. And so I get v final is equal to really the initial momentum of both objects added together divided by the total mass of both objects. So we can do some math now, plug in my numbers, and I get that v final, the final velocity for both the cars, is 1.1 meters per second. Now if we think about this for the second, does it make sense that the car that was moving faster is moving slower after the collision? Sure. Does it make sense that the car that was moving slower is now moving faster after the collision? Sure, that probably makes sense. Does it make sense that the velocities are closer to the velocity of the bigger of the two masses than the smaller of the two masses? Yeah, that probably makes sense. So let's look at another example. And here I have two skaters that are standing face to face at rest on the ice. The two skaters are going to push off one another and end up moving in opposite directions. One skater moves to the right with a velocity of 1.5 meters per second, has a mass of 85 kilograms. The other skater moves to the left from our perspective and has a mass of 55 kilograms. What we want to do is find the velocity of the skater that moves to the left. Now if they're both at rest initially, they both have 0 as their initial velocity. So I know 0 is their initial velocity, I know the masses of the two objects, and I know the final velocity of person 1. I don't know the final velocity of person 2. But let's apply conservation momentum to see if we can solve this problem. So if we write out what initial momentum looks like, it's m1v initial 1 plus m2v initial 2 equals m1v final 1 plus m2v final 2. Now it's worth pointing out that v initial 1 and v initial 2 are both 0. So the initial momentum of this system is 0. So 0 equals m1v final 1 plus m2v final 2. And I can now solve this for v final 2. Subtract m1v final 1 to the other side, divide by m2, and what we're left with is that v final 2, when I actually do my math, is negative 2.32 meters per second. So the negative says the person travels to the left, the 2.32 meters per second tells us how fast the person is moving. So in both these problems we use conservation of momentum, this relationship, to solve the problem. If you have two objects that look like it's a collision, either running into one another and bouncing off one another, running into one another, sticking to one another, in this case together to begin with and apart after something happens, conservation momentum is a great way to begin to work those types of problems.